All right, so today we are going to be going over more aspects of magnetostatics. So last time in class we talked about the total electromagnetic force, something called the Lorentz force. And the total electromagnetic force was a combination of the Lorentz force and the electrical force that we studied in Module 3. Based on the total electromagnetic force, there's something called the Hall effect. We spent a good amount of time on that. You'll have homework questions on that. The Hall effect is important because it's used in the magnetic field sensors that are used in your cell phones and industrial equipment. We started talking about magnetic torque, and we'll continue on that today because this has an important role in DC motors. The types of motors that are used in industry, the types of motors that are used in electric vehicles, the types of motors that are used in stepper motors, scientific equipment, toys, and such. Then we'll get into current-induced magnetic fields. So we'll talk about the Bio-Savart law, Ampere's law, and basically how you can calculate the magnetic fields in a variety of canonical geometries like a wire, a sheet, a loop, a toroidal coil. So we'll be doing some examples of that. Now this gets applied to electromagnets. One of the most important elements that's related to magnetostatics is the electromagnet, which is a device that creates a magnetic field when you run a current through it. If we have a little bit of time at the end, we'll talk about the magnetic properties of materials. So let's get right to it. Okay, so we are going to talk about motors. And we're going to give a context for our discussion of torque today in the context of electric motors. I mentioned this last time. I'll mention it again real quick. The Lamborghini 2020 Aventador. It's a V12 internal combustion engine. This car goes from 0 to 60 in 2.8 seconds. It's one of the fastest sports cars out there. It runs on gas, and it produces a torque of 690 newtons per meter. Gasoline engines produce maximum torque when they're at high RPM, so when the engines are already going at a certain speed. So when these vehicles are going fast, they generate the maximum torque. Electric motors, on the other hand, they generate their maximum torque when they're standing still. That's right, when there's 0 RPM and 0 motion on the wheel. So one of the interesting things about that is that the electric motors, they're designed, with certain specifications. They can have much greater levels of torque than gasoline engines can. So if you compare the Lamborghini, which is a top-of-the-line sports car, with the Tesla Model S or the Tesla Model X, which is an SUV, almost like a family car, these engines actually have more torque than the Lamborghini. And as a result of that, as I mentioned in class last time, you can see a lot of cool YouTube videos where you see the Lamborghinis being beaten off the drag race by some of these Tesla vehicles. It's pretty cool to watch. The Tesla Model S goes from 0 to 60 in 2.4 seconds. The Model X does it in 2.7 seconds. And these have massive amounts of torque, 50 to almost 100% more than the Lamborghinis. These two use these things called induction motors, which we're not going to be talking about in this class, but because it involves electrodynamics, dynamic fields, and we are talking about static fields this time. The Tesla Model 3 and the Chevy Bolt, which have slightly lower performance but still quite impressive, 640 Newton meters of torque for the Tesla Model 3. These use switched reluctance motors that have an internal permanent magnet in them. So some of the concepts that we'll talk about today can actually be used to understand these two types of engines. And so the main point I want to make on this slide is that all electric motors, whether they're induction motors or internal magnet motors, they're all based on the Lorentz force. So that gives you the importance of this basic and fundamental rule that we've learned thus far. So to talk about electric motors, we have to review the mechanical concept of something called torque. Torque is the force that would cause a body to rotate about an axis. So if you imagine this orange thing as a wheel right here, if we want to get that wheel to spin, we have to apply a torque on it. A torque is a rotational force. And the way that we define torque is equal to d cross f. So this is the vector definition of that. So this vector d is a vector going from the center of the axle, the center of the axis of rotation, to the side, to the place where the force is being applied. There's two ways you can think about it. You can think about an electric motor just applying rotational force to the wheel. You could also think about it as applying a linear force to the end of the rotational element. In other words, this F you could kind of think about as someone like literally putting their hand on the edge of the wheel and trying to push that down, and that would cause the wheel to spin. So that is the force F. The torque, which is again given in newtons per meter, is this t vector here. Now the t points along the direction of the axis of rotation. Okay, and the right-hand rule you can think about is that your thumb is going to point in the direction of the axis of rotation, and your fingers are going to curl in the direction of motion. So you can imagine your thumb is pointing out this way, and your fingers are curled in a counterclockwise direction like this. Okay? All right. So the d vector is a vector that points from the center of the axis out to the edge where this f vector is. And then the f vector, the force vector, is pointing tangential to the edge of the disk. Okay, and then there's an angle, theta, between these two vectors. All right, right now in this particular diagram, you can see that theta is equal to 90. All right, so it's the cross product of these two. As you know, the cross product is equal to the magnitude of d. Let me just jot that down here. This is equal to the magnitude of d, so in other words, the length here, times the magnitude of f, times sine of theta going from d to f. Right? This is the definition of the cross product. And then there's also the n hat vector. Right? N hat, this is the vector, unit vector, that is perpendicular to d and f both. Okay? This is all coming from the definition of the cross product. Okay, so this is the definition of torque. The way that you can intuitively think about this is that for a given force, if we keep force constant, the longer the moment arm, meaning the larger the d, the more torque will be applied. Okay? So the same amount of force over a longer d will provide a greater torque. Similarly, for this, if you keep d fixed but you put more force on here, there'll be more torque. All right? So let's do an example, a simple torque calculation. The radius of the disk is 1 meter. The force is 5 newtons in the negative y direction. Okay, so this is the same diagram as we saw before. So this force here is 5 newtons. Okay, and you can see that this is in the negative y direction. Y is pointing up. The distance here is 1 meter. Calculate the torque, assuming that the force is 5 newtons. So go ahead and enter your choices in this poll. I'll start the poll now. This has 5 choices. There we go. I'll just put the equation down here too, so y'all can don't have to refer back to the previous slide. Torque is equal to d cross f. go ahead and work on that. I'm just going to check on the questions here. Is torque newtons times meter or newtons per meter? It's newtons times meters. I apologize if I said that incorrectly before. Okay, so we have 13 out of 20 students responding. Let's wait a little bit longer for other folks to respond. All right. Okay, so it looks like 45% of the class answered B, 25% of the class answered A, and 10% of the class answered C. Correct answer is B. By the way, this should have been C here. Sorry about that. But this is the correct answer, B. All right, so the way that we solve this problem is our D is equal to 5 and negative 5 y hat. F force is equal to, force is equal to negative 5 y hat. Okay, let's erase this. So D, you can see that D is pointing in the negative x hat direction. So x is in this direction, D is pointing in the negative x hat direction. So, and the magnitude of D is the distance. So the distance here is 1 meter. And so we're going to say the magnitude is 1, and it's pointing in the negative x hat direction. Okay, and so the torque is equal to D times F, which is equal to the magnitude of D times the magnitude of F times the sine of the angle between them. And this is pointing in the n hat direction. So let's fill these in now. The magnitude of D is 1. The magnitude of the force is 5. The angle between them, you can see that this is 90 degrees, so this is sine of 90, which is equal to 1. And the n hat vector is, you have to look at the vector that is orthogonal to both of them. Now you have to use the right-hand rule here. Okay, right-hand rule, the first vector, so think about your index finger is pointing in the direction of D. So this is your index finger, middle finger pointing in the direction of F, and your thumb points in the direction of T. So think about your index finger pointing in D, middle finger pointing in F, and your thumb is pointing in the direction of T. And so the T is the z hat vector. Okay? So this is going to be 5 z hat newtons meter. Okay, I apologize for the mistake on this slide. This should actually, these are not newtons per meter. These should all be newtons times meters. So thank you for that correction. Appreciate it. Okay. Okay, yeah, thank you, Noor, again. All right, so that's a simple torque calculation. Let's move on to the next part here. So how do we get torque using an electromagnetic motor? We're going to do a simple example on this slide, and then we're going to go into a slightly more complex example on the next slide. Actually, it's actually the same example, but it's just looking at when the current loop is in the plane of the magnetic field in the first slide, and then we look at the more general case when it's outside the plane of the magnetic field. All right, so what we need to do in order to calculate the torque on a loop, we know that a current loop has 4 segments, okay? Now, just keep in mind, if this confuses some of you, like the loop wouldn't actually be connected quite like this. If you wanted to run current through a loop, you could connect this to a current source here. right? And this little section here would not have a connection there. Okay, that's if you want to run a current in a certain direction. So this part would be cut out. Okay, there are other ways you can generate current in a loop through induction, but we're not going to be talking about that right now. So let's just erase this for the time being. So just assume that you have current that's going around in a circle like this. All right, you have this 4 segments of the loop, and we want to find the total torque on the loop. So key point here is this is the pivot axis. So our direction of torque is going to be in this direction. So the torque vector is going to be pointing here, and the axis of rotation is going to be like this. All right, I'm just telling you that beforehand, so that'll give you a little bit of context. Okay, so this loop is going to rotate in that direction. All right, now, so we're going to start with looking at each one of these 4 segments. We'll start with segment 1, and then we'll go to segment 2, then go to segment 3, and then go to segment 4 at the end. So what we're going to do here is start with segment 1. Okay. Now, so what we have to do is go back to a relationship that we looked at earlier, thing that we ended off with on class last time. What is the Lorentz force on a segment of current carrying wire? So this is what we found. If we have a wire and a current is running through that wire, and that wire happens to be in a magnetic field, then there's going to be a Lorentz force on that wire. Okay, and the magnetic force is equal to I times the integral of dl cross B. Okay, and what we found is that, if we just jot this down really quickly from class last time, if we do this calculation on a straight segment of wire like this, which is the simplest case, the Fm is going to be equal to I times the integral of, in this case, z equals 0 to the length of the wire. And dl is dz times z hat. And that's going to be crossed with b, and b is pointing in the negative x direction. So b0 times the negative x direction. All right, and when you take the cross product of the two, you can refer to last time in class. Actually, we can just do this real quick. This is dz b0, magnitude of dz, magnitude of b0, times sine of the angle between them, and that angle, that was sine of 90. And then the n hat vector between them, as you put your index finger in the direction of current, that's pointing in the z direction, and your middle finger is pointing in the direction of the magnetic field, and so the n vector is in the negative y direction. Okay, and you integrate this from z equals 0 to L, and you get I times B0 times the length of the wire. This is the length of the wire, and it's just in the negative y hat direction. Okay, so this simple rule says if you have a straight wire like this, all you have to do to find the total magnetic force is to multiply the current times the magnetic field strength times L. Okay, and key thing to keep in mind, this was assuming that the angle, that the magnetic field and the direction of current are at a nice 90-degree angle. If this is not the case, then you have to add this sine term to it. So let's actually say sine of theta here. All right, so we can add that term in here. All right, so for the first problem that we're going to be doing right now, this is the simple problem. So we're going to start with this length of segment here, so the one on the left here. So this segment of wire has a length b. Okay, you can see that the vertical length here is b. So without even doing this integration well, I just did it there on the other slide, what we find is that this first force is equal to I times the length of the wire, which is small b, multiplied by the magnitude of the magnetic field, which is b0, and the direction is z hat. So let's quickly look at which direction z hat is pointing. I'm gonna just add some of this so you can see here that the z-axis, this is the top view, and then this one is the side view. So just so everyone's clear on that. Okay, so don't get confused, the fact that this y is pointing in the upwards direction here, but in this diagram is pointing into the page. That's only because this is the side view. So in the side view, the z direction is pointing up like this, the x is pointing to the right, and y is pointed into the page. All right, so in this diagram, the z-axis is going to be pointed out of the screen. All right. So what I want you to think about, just this F1 here. Point your index finger in the downward direction. Okay. Point your middle finger off to the left direction, and you'll see that your thumb is, the resulting force, the thumb is pointing in the z direction. Okay, so that's how we got this portion of it. Again, the magnitude of the force is equal to the current times the length of the wire segment times the magnetic field, and that's in the direction can be found using the right-hand rule. So we have a force equal to I times force equal to this on the left side. So force 1. So that's on this side. If we apply the same analysis to the third one, the third side, going up like this, the difference is that the current is going in the opposite direction. So imagine your index finger pointing upwards like this. So you can, I do suggest that you just try this at home. The more you do this, the more practice you get at this, the better off you'll be. Point your index finger in the direction of current here with number 3, and point your middle finger off to the right, where the magnetic field is pointing. Your thumb is going to point into the screen. All right, so that means it's the negative z-hat direction. So that's why you have a negative sign here. All right, so F2 and F4, if we look at these two segments, what you'll find is that the force along these two segments is 0. So the question is why? So maybe someone can type into the public chat, why is the force on segments 2 and 4, why are they equal to 0? Hamza is typing, Falak is typing. Exactly, you got it. Sine of 180 and sine of 0. So the force on a segment of wire is equal to the length times the current times the magnetic field times the sine of the angle between the magnetic field and the current. That's what we just found on that slide. And then the direction of that force is n hat. So in F1 and F3, the theta is equal to 90. There's a 90-degree angle between the direction of current and the magnetic field. So you can see that here in 1, there's a 90-degree angle here. There. In 2, there's a 90-degree angle here. But in the case of 2, if we look at this section here, where this area here, you can see that the current is going from right to left, but the magnetic field is pointing in the opposite direction. So in 2, theta is equal to 180, and then in 4, the theta is equal to 0. So in these two cases, the force 2 is equal to force 4, and they're both equal to 0. right? Because the magnetic field, the sine of 0 is 0, sine of 180 is 0. Basically, when the direction of current is in the same direction as the magnetic field, you do not get any Lorentz force in that case. All right? So the first part of the problem is to calculate the forces on the segments 1, 2, 3, and 4. So this is step 1 here. Then we go to step 2, is we have to figure out the torque. The torque can be found by adding up the forces on each one of the moment arms. We treat each one of these guys as moment arms. So let's simplify the problem first. We know that the force on 2 and 4 are equal to 0. No force contributions there. To figure out the torque due to 1 and 3, this is what we have to do. So you bring in the side view. So now we're looking at the side view here. And this red dotted line should connect the two diagrams together. This is the axis of rotation. Okay, but now we're just looking at the side view. So in the side view, you have the current. So this is loop 1. So this is the segment 1, and that is corresponding to this point here. Imagine that the current is going out of the page. So it's coming out of the screen. That's what that point means. Across means that it's going into the screen. So imagine that the current is coming out of the screen here, and you're going to do your D cross F. So D1 cross with F1. Okay, so that's the first portion of the torque. So a part of the torque is coming from the force on segment 1, and an additional torque is coming from segment 3. Okay, so you have two segments that are contributing to the torque, and to find the total torque, you have to add them up. All right, so in the first one here, the D1 cross with F1, so we're going to be doing D1 is equal to negative x hat A divided by 2. Okay, where did this A divided by 2 come from? Well, this is the length. A represents the length going from one side of this loop to the other side of the loop. But if you look at where this is the axis of rotation, 0. So the length from the axis of rotation to the loop arm is A over 2. All right, the distance from the axis to the loop arm here is A over 2. So that's where the A over 2 comes from. And then we figured out the forces previously. All right, so you take the cross product between these two. You add to that the cross product between these two. And what you'll find is that both of these, this cross product here results in a vector in the y direction. The axis of rotation is in the y direction. This second portion here also contributes a torque that results in a torque in the y direction. Okay, now think about why that is. Just if we look closely at this diagram here, just think about a rotating element. Think about this as a seesaw. Okay, so this is the fulcrum of the seesaw here. On one end of the seesaw, you're applying an upward force. On another end of the seesaw, you're applying a downward force. So both are contributing to try to rotate this thing along in the clockwise direction. Okay, if F3 happened to be pointing in the upwards direction, the two torques would cancel each other out, and you would have no net torque. But in this case, you can see that you have one force going in this direction, one force going in this direction. So the two torques add up, and there's some force, there's some torque is used to rotate this about the axis, rotate the motor about the axis. Okay, so adding up those two components, you can come up with this equation, y hat I A times B B0. So A is the length, B is the width. Multiply those two together, and you get the area of the loop. So the two observations that we see from this equation is that the torque, first of all, the upward force on one end of the loop, there's a downward force on the other end of the loop, so both of this contribute to torque. And this result here, y hat IAB0, the torque scales with the current and the area of the loop. So if you increase the current in your loop, so you're supplying more power to your motor, you're going to get more torque. It's linear. All right, and then the area of the loop. So that means the larger the loop in your motor, the more torque you're going to generate. And the third part here is the magnetic field. The stronger the magnetic field, the more torque you're going to get in your motor. So, many of you are probably going to end up working in the automotive industry. You can already start to think of how something like this can help you if you happen to be part of a design team of a motor. What are the levers that you can tweak as an engineer to get more power out of the motor? And what are the trade-offs? Like if you're designing a motor, of course, you're going to think, oh, well, I'll just put more current in there. Well, the problem with more current is you dissipate more power. You're going to drain your battery more quickly, and you're also going to generate more heat. So you need to deal with both of those issues. Well, you'll say, okay, well, why don't I just make the area of the loop bigger? Well, that's going to increase the size of your motor, and that's also going to increase the weight of your motor and the size of your car. So this is also something to think about. Then you might think, oh, well, I'll just put a stronger magnetic field on there. Some of these magnetic fields can come from magnets, and as you know, we're going to find out that the electromagnet generates more power. The more generates more magnetic field, the more power you put into it. Or if you use a permanent magnet motor, you can just use the strongest magnetic material you can find, which is right now they use like neodymium magnets, which is rare earth magnets, and they try to make this B0 as strong as possible. All right, so let's take the simple example now. This is a simple example. We calculated the torque on the wire when the loop happened to be in this position. All right, but we know in a motor that the loop it's not stationary. The loop is going to be rotating. All right, so this is a real, a closer example of what a motor might look like. The loop actually will rotate because of the torque. The loop will rotate about the axis, and but as it's rotating, it turns out that the torque is actually going to change depending on what the position of the motor is. So this is a very simple motor where you have a single magnetic field and you have a single loop of current. And so let's see what happens. So this is the diagram that we're looking at now. Again, just like before, this is the 3D view, and then this is the side view. All right. So we can go through this entire derivation again, but I'm not going to do that in the interest of time. I'll just tell you that these forces that we derived earlier are the same as before. Okay, F1 and F3, we already calculated them. F2 and F4 exert no torque. Why are these the same? They're the same because the direction of current, the direction of the current and the direction of the magnetic field are always still orthogonal to each other. Okay, this is still this blue arrow that you see here and the green arrow that you see here, the magnetic field, they're still 90 degrees if you measure the angle between them. Okay, so nothing's changed there. The difference is that this angle theta changes. So we're talking about this angle here. I've just circled. All right. So when that angle changes, are you guys able to see my mouse? I guess not. Okay, so let me turn on the laser pointer. So this angle here is changing. It turns out that as that angle changes, the torque is going to change. Why? To understand why, we have to look at this diagram down here. Now we're in a situation where the loop is at some kind of angle. All right, and when theta is equal to 90 degrees, that loop is just flat across like it was in the previous slide, but the angle can change as well. Okay, and what we talked about earlier 2 slides ago is that when we add up the torque vectors here, we have these cross products. And whenever you have a cross product, you have to consider the angle D, the angle of D going from D to F. If you look at this diagram closely now, you're going to see that, actually I should write on here. Uh-oh. Okay, 1 second here. Okay, that should be better. So your D is the direction of going from inside to outside. So your D is here, and your F vector is here. All right, so there's an angle between them now. Before that angle was 90 degrees. Now that angle, it looks like it's more than 90 degrees. All right, so we're going to call this alpha, so there's no confusion here. So this angle between them is alpha. And so the way that you can see in this diagram here, so the way you see in this diagram here, this this alpha and then this theta are related to one another. Okay, so this is 180 degrees. So alpha is equal to, theta is equal to alpha 180 minus alpha. Okay, and I'm just going to put this here. You can prove it to yourself. The sine of alpha is equal to the sine of theta. Okay, you can remember this from your geometry classes that two angles that sum up to 180 degrees, the sines of those angles are equal to each other. So that's why this theta, that's why the sine of alpha is actually equal to the sine of this angle here, this theta here. All right. So without going into all the details of it because of the interest of time, there's actually not much more detail to go into, but basically this comes out to this equation here. All right, the torque is equal to n hat. So n hat is the direction of rotation. So let's say y hat I times a times b0 sine of theta. So the torque depends on this angle theta. When the arm is flat like this, you reach a maximum. And the question I'll ask here as a polling question: at what angle does the force become 0? So I'll just put that out as a polling question. So as this motor is turning, at what angle theta does the torque become 0? Oh, and I just realized there's actually 2 correct answers here. All right, just wait a few more minutes. Looks like we have a question on the chat. Let me check that. Can't see the choices. The choices are on the bottom right corner in the green box. Right here. Oh, looks like we have some more questions. Let me check those. It's covered? You're not able to see where it says polling question on the bottom right side? Oh, I see what's happening. Got it. The pop-up poll is covering it. Got it. Okay. Well, I have a quick solution to that. Just move this up like this. Hopefully that should help. All right, you should be able to see it now. And as some of the other students pointed out, if you go full screen, then you'll be able to see it as well. All right, let's see where we're at. 18 out of 21 have responded. Okay, so we actually have an even split of A, B, C, and D. Correct answer, there's actually two correct answers, A and D. All right, so this theta here is what you're thinking about here. When this theta is, sine of theta reaches a maximum when when its theta is 90. So when theta is 90, it'll reach a maximum torque, and it will reach a minimum, so when it becomes 0 or 180 degrees, because sine of 0 is 0, sine of 180 is 0. Okay, all right. Okay, so then moving on. So we have this, this is the torque that you get from just a basic single loop motor. And you can also define the torque in terms of the magnetic moment. M is equal to N hat times NIA, and then torque is equal to M times B. So this is something you probably don't need to know for an exam, but a lot of times that in motors they define the torque in terms of a magnetic moment instead of in terms of this explicit formula here. It's the magnetic moment is sort of a figure of merit for a particular motor design. Just for a little bit of applications, I thought you might find this interesting. This concept is used in a basic brush type DC motor, which was used for many years. It's used a little bit less frequently now because of the reliability, but I thought you might find this interesting. The key concept in a DC motor is that you have this loop that you saw here just previously, and you have a magnetic field going from left to right, so identical to what you saw in the previous two slides. And then you have a current running through the system, right? And as a result of that force, this results in a motion of the motor, a rotation of this loop. Now the key thing about the brush DC motor is that you have this thing called a commutator. In order for the motor to keep on rotating, you have to keep the torque going. All right. So when the loop is in this position, I'll draw it up here. So we can see real quick, just from the right-hand rule, that we are going to get a torque that is upwards on this side, and it's going to be downwards on this side. And we can just double check that real quick with the right hand rule. Nope, I actually got it incorrect. It's always good to check yourself. So if you use the right hand rule, your index finger points in the direction of current, magnetic field points in the direction of your middle finger, thumb points in the direction of the force. So your force here is going to be in the downwards direction, the force here is going to be in the upwards direction, and so your torque is going to be in the clockwise direction. All right? So then the thing starts to turn. Now, if you don't, the problem is if you don't change the direction of the current, let's say this thing turned, and now this side of the loop is now on this side. So when this thing turns 180 degrees, the force on the left-hand side of the arm is now going to be down instead of up. So the torque is actually going to change directions. So if you keep the current going in the same direction in the loop, the most that the loop will turn is just 180 degrees. It'll turn 180 degrees and then it'll stop. It'll even turn less than that. In order for you to keep the torque going as the motor turns, is that you have to reverse the direction of the current. Every time it rotates 180 degrees, you have to reverse the direction of the current. And that is the job of the commutator. So the way the commutator works is that you imagine just having like a piece of metal like this, a piece of metal like this, and as the loop turns, the two ends of the loop switches the direction in which it's connected to the battery or the circuit. All right, so when the loop is in this position, the current goes this way and it travels in the counterclockwise direction through the loop. And when the loop changes direction, when the loop turns over, then the loop is connected in the opposite polarity. All right, so let's just look at a quick YouTube video here. I'll just pull this over. And since we don't have the audio here, I'm just going to, just a moment. All right, let's skip the ad here. All right, let me make this a little bit smaller. Sorry. All right. So it's just, don't worry about this right now. This is a more complex motor. All right, so the simplest one looks like this. These are the commutator rings. Magnetic field is pointed from left to right, and then you have a coil that's going in this direction here. There's two rings here. If you look closely, the two rings are actually not connected to each other. It's not one contiguous ring. It's just a half a ring here, a half a ring here. And this is connected to the battery source like this. Okay. Electromagnetic force is induced, causes a torque, coil starts to rotate. And the key thing you want to notice here is when the coil rotates, now the commutator rings connect to the source in the opposite polarity. So the direction of so on the left side, the current always flows away, and on the other side, the electricity always flows towards. This keeps the torque going in the same direction, and that keeps the motor rotating. All right. The second concept that they're pointing out here is that when the coil is at 90 degrees at a 90-degree position, you'll notice that the magnetic field is pointing in this direction, going from left to right. Your current is pointing out of the screen, and your force is going in the upwards direction. So when you have a situation like this, there's no torque on the wire because you have a force vector pointing upwards, another force vector pointing downwards. And these force vectors are in the same direction as your D. So in this position, there's no torque on the wire. When it was in the horizontal position, sorry, let me back up here. When it's in the horizontal position, you get maximum torque. But when you are then in the vertical position, the torque goes to zero. So that's one of the key issues with a single coil motor. To get around that, what they do is they have multiple coils, right, and multiple pairs of commutator rings. All right, so that way you keep the torque going, even when you're at that 90-degree position. All right, so this is called a brush DC motor because you have the commutator rings rotate, and there's the way the coil is connected to the commutator rings through something called a brush. This type of motor has some issues with reliability because the brush can get worn out over time. It also has some extra resistance. So there's other motor designs that are used instead of it. The commutator rings are essentially used to switch the current going from one direction to the other in this coil. Instead of using commutator rings, you can use position sensors. Position sensors like Hall effect sensors that I showed you earlier. So once the motor gets to a certain position, there's an electronic circuit that will switch the current rather than this commutator ring being responsible for switching the current. So those are called brushless DC motors. All right, so in any DC motor, you have current running through the loop, and whenever you have current running through a wire, you obviously get some heating. And so the amount of electrical energy that you put into it, some of that electrical energy is lost to heat, and the rest of it is converted to useful torque. And electric motors can have fairly high efficiency depending on the design of the motor. So the different motor designs will have different levels of efficiency, but they can be as high as like 85, 90%. So that's pretty good. All right, moving on then. There's any questions on DC motors, on the brush DC motor? This is a really nice animation and a video. So I highly suggest that you just click on this link in your notes and just watch that. You'll get a good understanding about how these things work. The animation here is really great. It does a much better job than the narrator describes it really well, much better job than even I'm doing. So I think that I recommend that you watch that. All right, what you're going to be responsible for in this class is, like, you're going to have a homework problem where you're asked to calculate the torque on a motor like this. I expect you to know really well the direction of the torques, the direction of the magnetic fields as this thing rotates. Those are going to be the types of questions I expect you to know. I probably won't expect you to know all the details of how every different type of motor works. For example, we're talking about synchronous motors here. I don't expect you to know the details of all this stuff. This is more just in the interest of so you know that there's other motor types out there than the basic DC motor that you saw. There's a term called synchronous motors, and synchronous motors, a certain type of that is a switch reluctance motor. Synchronous motors are where you have essentially a rotating magnetic field, and you have a permanent magnet that's inside the motor. So every motor has something called a stator and a rotor. The stator is the part on the outside that doesn't move. So stator, stationary, doesn't move. That's the way you can think about that. And on the inside part of the motor, this is the part that rotates. That's why it's called the rotor. All right? So in synchronous motors, what happens is that you have magnets on the stator portion, and the stator generates a rotating magnetic field. And one way you can do that is, like shown here, you could have one electromagnet that's oriented at a certain angle, another electromagnet oriented at another angle, a third electromagnet oriented at a third angle. So as you supply power to these three magnets in succession, you can create a rotating magnetic field that way. And if you have a rotating magnetic field, then if you have a high magnetic permeability or a magnetic material in the middle, that magnet is basically going to rotate along with the external field. So this is how the synchronous motors work. Now, the simple way you can think about it is that if you have a permanent magnet on the inside and you have a rotating magnetic field, of course the magnet rotates with the field. But there's also this concept of reluctance. Reluctance, as you can think about, is kind of a magnetic circuit. Okay, this creates a magnetic field. The magnetic field lines, if it goes through a high permeability material, there will be less reluctance if the magnetic field is going through a high permeability material. If it's not going through a high permeability material, meaning like here it has to go through air, it's passing through air and only a small portion of the field is passing through the high permeability material, that there's going to be a higher reluctance here. And when it's aligned, there's a lower reluctance. And the laws of physics will be such that the energy will be such that the motor will want to align in the low reluctance state. All right, so this is an example of a magnetically permeable material aligning with the electric fields. So you can think about it either way. The simple way is just think about this as a permanent magnet, or the more correct way is think about this as a reluctance. All right, so the advantages of these types of motors is there's no brushes or commutator rings. These are higher efficiency than the induction motors that are used in the Tesla Model X and Model S. But the disadvantage is that the current versus torque is nonlinear, and you get a little bit of ripple in the torque, meaning like a non-uniform torque. So because these are higher efficiency than the induction motors, this is one of the reasons they are used in the Tesla Model 3 and the Chevy Bolt. Another one is that if it's designed the right way, these things can actually are simpler and lower cost than the induction motors. All right. So you could read about this more. You know, there's a lot of hoopla about the Model 3 and how it had its interesting design of a switch reluctance motor. But this is the basic concept. So in these types of motors, again, you have a rotating magnetic field and you have an electronic circuit that supplies power to 3 different electromagnets in succession so that the magnetic field kind of rotates with time. All right, so moving on now, how do I calculate a static magnetic field? So we're changing gears now. We're not talking about motors anymore. Now we're talking about how do we actually generate a magnetic field. So the context I could kind of give you to relate this back to what we were talking about earlier is that, you know, this is an example where we use an electromagnet. So there's some coils here, there's some coils here, and when we run current through that wire, we can generate a magnetic field. So this section, we're actually going to talk about how do you calculate the magnetic field due to a current running through a wire. And so there's 2 strategies that we often use, and you'll have some homework questions on this. The Bio-Savart law. This is the brute force approach, if you will. The Bio-Savart law adds up the current densities to find the total magnetic field. We'll talk about that. Basically, whenever you have a flowing current, it's accompanied by a magnetic field. Ampere's law is a shortcut that you can use. Bio-Savart law takes integration, and it takes it takes a lot of work to do these problems. You'll see. Ampere's law is a shortcut. Is if there's symmetry in the problem, you can use Ampere's law by drawing an Amperian contour to find the magnetic field, and we will talk about that. So let's get right to it. The Bio-Savart law states that whenever you have a current traveling through a wire, it's going to generate a magnetic field. The way you can think about it is that imagine a current flowing through this orange-colored wire. Your thumb is pointing in the direction of the current. Your fingers are going to curl around in the direction of the magnetic field. So the magnetic field is going in this counterclockwise direction here, as you see here, and that's the H. Okay, thumb pointing in the direction of the current, fingers curl around in the direction of the magnetic field. That's what the Bio-Savart law says. Now, the Bio-Savart law is for linear current densities. So this is when we have when we just have current going through like a linear wire. This is the rule that we'll use. H is equal to 1 over 4 pi, and the integral of dl cross r divided by r squared. What does that mean? Qualitatively, what that means is that each little segment of wire, this little segment here, and the segment of wire right next to it, segment of wire right next to it, the segment of wire right next to that, all of these little segments are going to generate their own magnetic field. And the total magnetic field is that we have to sum up the contributions of every little segment as we go from left to right along this wire. Okay, so whenever we add up the different contributions, we're essentially integrating. So that's where that integral comes from. Okay, now we're not going to derive exactly where this r squared term came from and where the dl cross r came from, and where the I over 4 pi came from. We're not deriving the Bio-Savart law. I'm just going to teach you how to use it for solving problems. Okay. There's 2 other forms of the Bio-Savart law. That you have a volume current density. So if we actually consider the current density vectors, here we just considered the total current. Now, if you have non-uniform current density along the cross section of a wire, you'll use this one. And if you have a surface current density, you'll have a problem like this in your homework. The surface current density, you're going to use this form of the Bio-Savart equation. All right, so let's do one example of a linear conductor. So the question is, what is the magnetic field generated by a segment of wire carrying current? All right, So let's, we're going to do this, we'll do this problem. Actually, I'm just going to show you, I'm going to show you how to set up the problem, and then we'll spend a little bit more time on the second example, because this one, there's actually, turns out there's a lot of math involved in this problem. So I want to show you the strategy of how to set it up, and then we'll just show you the results at the end. All right, so the strategy in these problems is that you're going to find, as we found in the previous slide, here, in fact, let's just copy this over. All right, so this is the Bio-Savart law here. And so what we need to do is solve it in piece by piece. All right, first we find dl, then we find r, then we find dl crossed with r hat, and we determine the limits of integration, and then we integrate to find the magnetic field H. So I'm going to show you some parts of how to set up this problem, and then I'll show you some of the results on the next slide. I'm just going to move this over to the left here. That way we have enough room to work with. Okay. So the first step is to find dl. So we have to look at the geometry of this problem. Okay. In a linear conductor, imagine that you have a wire oriented on the z-axis. The current is going from bottom to top. And that we break up that wire into small segments like this. And the small segments are shown in red here with the dl. Okay. Our observation point is out here, out on the x-axis. And notice that the magnetic field is going into the page. How do you know it's going into the page? Apply the right-hand rule. Okay, when you apply the right-hand rule, your thumb is pointing in the direction of current. Okay, so your thumb is pointing upwards in the z-axis, and your fingers are rotating around. So the direction of the magnetic field is going to be in this counterclockwise direction around the wire. So at this observation point, the magnetic field is going to go into the page. All right, so I'm going to show you how to set up this problem. So the first part is the dl. You have to find what dl is. So in order to find what dl is, you actually have to think about the limits of integration. So it might be better to just do these two together. So you have to consider we're going to be integrating along this entire segment of wire. All right, so if you think about the integration as we go from one side of the wire to the other, think about you're probably going to be integrating in the z direction. All right, so if you're integrating in the z direction like this, then your dl is going to be equal to, the direction is z hat, and the magnitude is just dz. All right, second part here. Now we're going to figure out what r is. R is the vector connecting the two, connecting the observation point to the segment of wire. Okay, so I'm going to zoom in here so you can see this better. All right, this is the observation point here. What you have to do is draw a line connecting the observation point to the little segment of wire. Okay, and that is your distance r. Okay, the vector, so the vector r points to, it points to the observation point. So it points from here, and it points from here in this direction to the observation point. The unit vector r hat just continues on like that. Remember, the unit vector has the same direction, but just a magnitude of 1, and so it's pointing in this direction. This is to highlight the fact that r points from the location of the current to the observation point. dl is in the z direction, as you can see here, so that gives us a little bit of an orientation. And you have this this angle theta here that forms the angle between r and the z-axis. So so we can write out what this vector r is. Right? A vector has two components. You go in the up direction and the right direction. So this vector r, we have to go up and then across. So it's going to be so this is at some, imagine that this dl is at some point z. Okay. So in order to get from this location of the current to the observation point, we have to move up z, and then we have to move outwards by a distance of r. So z times z hat plus r times x hat. Or we can do this in the cylindrical coordinate system. We could say r times r hat. Right? So that's our r vector. So after this, now we can also find the magnitude of r. The magnitude of r, which we're going to need, because the magnitude of r appears in the denominator here. The magnitude of r is the square root of z squared plus r squared. Right? So that's the length of the vector here, going from the observation point to the location of the current. And then so our r squared, which is the denominator here, r squared is equal to z squared plus r squared. Okay. The third step here is that we have to now look at dl cross r. All right, so this is equal to the magnitude of dl as magnitude of r. Oh, I'm sorry, it's dl cross with r hat. There we go. Sine of theta going from dl to r. And then the vector that they're both perpendicular to by the right-hand rule. So the magnitude of dl is dz. The magnitude of r hat, it's a unit vector, so the magnitude is just 1. Sine of theta going between them, this is the part where you have to look at the geometry. Okay, this is where this angle theta comes into play. So I'm just going to draw this here. The angle here is equal to theta. That's the angle between dl and r. And the n hat direction, so the unit vector where the resulting magnetic field is pointing, that's in the phi hat direction. You can find that by the right-hand rule. All right, so we've set up our dl cross r. This is equal to sine of theta dz times phi hat. All right, the fourth part, our limits of integration. We are going to be integrating from the bottom of the conductor to the top. So our z is going to go from negative L over 2 to L over 2. Right. And then the final step is that we'd actually have to integrate. Now, this is the step that I'm going to omit in the interest of time. But on a test like this, I want to show this as an example. If you run out of time and you don't have time to perform the integral, if you show these key steps, you'll receive more partial credit. Okay, I know some students did that on the previous exam and some students forgot to do that. Lay your steps out, show me that you know how to do the problem, and if you're not able to do the full integration, you'll still get points on it. The solution to this, the reason I'm not doing it in class here, because it turns out that the mathematics here, it's not like super difficult, but it just gets really long. So we're going to omit that here, and we're just going to look at the result. Okay, so it turns out that the result is if you have a short segment of wire or an intermediate segment of wire, then this is your relationship for the magnetic field. Actually, let me be more specific. This is the magnetic field assuming any length of wire. Okay, you see that there's an L factor here, there's an L factor here. The radius is the distance away that you are from the wire. Again, this is your result for the magnetic field. Now, an important result is that when L becomes very, very large, so when L goes to infinity, this result here simplifies to what we saw probably in lecture 1. This is the magnetic field coming from an infinitely long wire. And it simplifies to just just two terms here, I over R, and then you have a 2 pi there. All right, so the direction is in the phi hat direction. It's going into the page, and the magnetic field is proportional to the amount of current you have, and it falls off as 1 over R. All right. The second example that we'll do here is for a circular loop. All right, and this one has, actually we're running out of time here. We have hour and 51. Okay, we have about 20 minutes left in the class, so this may also be one that I will just set it up for you, and then the math you can actually try to do on your own. This is actually an easier problem to do, but the setting up is more tricky. So what I'm going to do is just copy this over to the next slide here. All right. So we're going to follow the same procedure as before, except we have a slightly different problem here, slightly more complex problem. So now we have a loop of wire, a single loop, circular loop, and our observation point is up here. Now, the way I like you to think about it is that assume that, wherever you have a little segment of wire, you're going to have a rotating magnetic field around it. Right? So out here on the wire, the rotation is going to go like this. And on the other side of the wire, it's going to look like this. One of the key points I want you all to understand, this is really important because this is how you create an electromagnet. One of the key things that you notice here when you have a circular loop like this, if you're running current through that loop, all right, just by using your right-hand rule, you can notice the direction of the magnetic field due to this side of the loop and then due to this side of the loop. What you notice is that inside of the ring, inside of the loop, the magnetic field vector is pointing upwards. It's pointing upwards on this side. It's also pointing upwards on this side. So interestingly, when you have a loop like this, the magnetic field vectors, they add up. As you're going around the loop, the magnetic field components, contributions, they add up. And what happens at the inside of your loop, you get a strong magnetic field that points in the upward direction. If you reverse the direction of the current, then the magnetic field will point in the downward direction. The main point is that you're concentrating the magnetic field in the middle, and all the magnetic field vectors point in a single direction in this type of circular loop. So I just want to quickly do this derivation, but the key concept is what I've already explained to you. If you have a loop, you get magnetic field pointing axially inside. And if you have multiple loops of wire, you're going to have more of that effect. So you know how if you want to build an electromagnet, you just have many loops of wire coiled around some kind of magnetic material in the middle. You have that coil, it's called a solenoid coil. Well, that is just to create more and more of these turns, and it creates more and more magnetic field contributions the longer your wire is. All right. So if I jump ahead, if you know like what a solenoid looks like, you're going to have a problem like this in your homework. Is you'll have the magnetic field goes through the solenoid like this. Inside the coils, you get a magnetic field vector that points upwards like that. All right. So, so the way you set up this problem, dl in this case is dl is equal to a times d phi. right? You're in a cylindrical coordinate system, so your dl is going around a circle. So in the cylindrical coordinate system, this is the radius, and then here's your d phi. Second part here, r is the vector that connects your current to the observation point. Your observation point is up here, and this vector r connects the two. So this r vector, you're going to go inwards in the r hat direction, so you're going to go negative a times r hat to get to the center, to get to the z-axis, and then to that you're going to add z times z hat. All right, so that's just a vector that goes inwards and up. The magnitude of r is equal to a squared plus z squared. And okay, so then the next part here is we can do dl cross r. All right, the dl cross r is equal to the magnitude of dl times the magnitude of r hat. I always forget to put the r hat. Okay. Sine of the angle between them, and then this n hat vector here. So the dl is equal to a times d phi. R hat is equal to 1. The angle between them is this angle theta up here, so sine of theta. And then your n hat vector. Now this one is where you have to think about the symmetry of the problem. So if you were to point, you take your first finger and you point in the direction of dl. dl is going around like this, okay? It's going in the theta hat direction. And then your r is pointing, your middle finger is pointing in the direction of r. So your thumb is actually going to be pointed outwards like this. I'm sorry, you do this at the observation point. So your thumb is going to be pointing in the outward direction like this. So the magnetic field, so your dl cross r is actually going to be pointed in that direction. Notice that this has an r hat component and a z component. All right. So if you were to actually write out both, you'd find that this is equal to sine of theta times r hat plus cosine of theta times z hat. Okay, if you consider both the r and z components of that. And a key part of this problem is that the r hat component can be ignored. Just like the electrostatics problem that we did when we had a ring of charge, there was symmetry, so this radial component disappeared and you're only left with the z component. That's the same thing that happens in this problem. So you're only left with, you can ignore this radial component. It makes the math easier. If you left it in, you still get the same result. They'd cancel out, but you just have to end up doing a lot more math. All right. So this theta is this sine of the angle dl and r. If you think about this, they're actually perpendicular to each other. So this one will actually go to 1. So let me just correct that. This theta is equal to 90. This angle between these two vectors is equal to 90. But this one up here is the one that you have to think about. That comes into your n hat term. And so your dl cross r ends up being a times d phi times a over square root of a squared plus z squared. Limits of integration in this case, you're going to be integrating all the way around the circle. So your limits of integration are phi is equal to 0 to 2 pi. Okay. Now I know I went over that relatively quickly, but I think if you could watch the video again, you can go through it yourself, and that may be helpful. I just want to show you the last step here. You can just integrate and actually find the field. So H, by the Bio-Savart law, is equal to I over 4 pi. Integral of dl cross with r hat over r squared This will be I over 4 pi. We are integrating around the circle, so we're going to be integrating from phi is equal to 0 to 2 pi, and we're going to be integrating this dl cross r that we found here. All right, so this is, oh, I forgot to bring that down, cosine of theta times z. All right, this is a squared. You notice we have two a terms here, d phi, and this is in the z hat direction. And on the denominator, we have r squared. So the square root term is a squared plus z squared to the 1/2, and we have to multiply that by the magnitude of r squared. So on the denominator, you've got a squared plus z squared to the power of 3/2. And when you do this integral, the only thing that you really have to integrate is this d phi. Right? All these are not a function of phi at all. So all you have to integrate here is the d phi, and you end up getting a 2 pi term there. So the final answer is I over 2 a squared plus z squared to the power of 3/2. Okay, so this is an example of where you can do the entire problem. You see that the magnetic field is in the z direction, so it's going up like this. In the middle of the coil, you get a nice magnetic field that's going straight through the coil. Okay, all right. So I hope that also showed you that these problems can be, fairly challenging, because there's just a lot of things that you have to think about. There's a lot of vectors you have to think about, drawing them out and such. There's another a shortcut to this, Ampere's law, and that's what I want to spend the next 10 or 15 minutes on. We'll just go a little bit over today. I hope that's okay. Ampere's law is the analogy of Gauss's law in electrostatics. Now, I'm saying that it was an analogy because Gauss's law was a way to simplify electrostatics calculations. It's a way for you to find the electric field when you have a charge distribution if you have symmetry. All right, you remember those problems from your last homework. If you have symmetry and you can apply Gauss's law, then you don't have to go through that entire integral, which is time consuming and can be painful. So Ampere's law is the analogy of that in magnetostatics. All right, it's easier to use than the Bio-Savart law, but it requires symmetry. So let me just quickly go over what the equation is, and then we'll go over how to use it. So it's derived from the fourth Maxwell equation. Del cross H is equal to J. And what we do is we integrate both sides. So we come up with an integral form of this equation. So we're going to take the integral over an area, over a surface area. So we take the integral of del cross H over a surface. So double integral, and you have a ds here. Do the same thing with J, double integral and ds here. When you take the double integral of, when you integrate the current density over a surface, you get the total current. All right, and on the left side here, this integral here, the surface integral of del cross H by Stokes' theorem, this becomes the line integral of the magnetic field around the contour. So H dot dl, the dot product of H dot dl going around a closed contour. All right, so this is using the Stokes' theorem. All right, so this is Ampere's law. So the question is, how do you apply it? All right, you're not going to need to know how to derive Ampere's law. You're going to want to know how to use it. So the first step in applying Ampere's law is to choose an Amperian contour, and the current I should go through the surface enclosed by the contour, and the magnetic field should be constant or zero everywhere on the contour. The best way to understand this is to actually by doing a quick example. Once you have the Amperian contour, you can use this equation here to solve for the magnetic field. So again, this is best way to do this is by an example. So let me describe what we have here. So when choosing an Amperian contour, you start off with some kind of current distribution. All right, just imagine that in this example we have current going through a wire. So a single wire that's shown in red. And so you see where this red circle is. That means that the current is going out of the screen, right? That dot there means that the current is coming out of the page. So the first step in choosing an Amperian contour is that the current I should go through the surface enclosed by the contour. So we have to draw a contour around this. And the second one is that you should choose the symmetry of the contour so that the magnetic field is constant or zero everywhere on the contour. So that's the first step. So can you choose, so the first polling question here, I'll start a poll, and you can choose A, B, or C. Which is the best Amperian contour to use? A, B, or C? It has to meet both of these criteria. The current I has to go through the surface enclosed by the contour. And the second rule is that you should draw the contour such that the magnetic field should be same everywhere on the outer surface. Or zero everywhere on the outer surface. Okay, good. I see that almost everyone chose A. That is correct. All right, the first criteria is met. This has to go, the contour has to enclose the current. All right, you can see that in C, it does not enclose the current, so this is not a good Amperian contour to use. Second condition, the magnetic field should be constant or zero everywhere. If you draw a uniform radius around the current source, then you have a similar magnetic field everywhere on the contour. This is one of those situations where you kind of need to know, you have to have an intuition for what the field lines are going to look like. Okay, all right. So the field lines, as we know from a wire, it goes around like this. This is not correct because a field, you'll have a small field out here and a larger field here. So it's better if the current is constant or zero everywhere in the contour. All right, so Ampere's law, applying it to an infinitely long wire. I'm just going to go show you the solution in the interest of time. The first thing we did is that what is the question is what is the magnetic field coming from an infinitely long wire? Oh, I can't see. We have a question here. Oh, okay. All right, no problem. So we chose an Amperian contour, a uniform circle going around where the current is flowing. So we selected an Amperian contour. Now the second step is using Ampere's law to solve for H. So we set up Ampere's law like this. The integral in a closed contour of H dot dl is equal to I. This is the line integral of the magnetic field as we go around the surface of the contour. So our, there we go. So the dl, so we are integrating phi is going from 0 to 2 pi. We're going all the way around the circle, and we are integrating h dot dl. So h is equal to h phi, some constant, and it's in the phi hat direction. dl is equal to r, the radius of the circle, times d phi, and this is in the phi hat direction. Okay, h dot dl is equal to h phi times r d phi. And then we integrate that. When we integrate that around the circle, we just get h times r times 2 pi Right? You see how simple this calculation was. All we did was did a line integral going all the way around the circle like this. And so you get h times 2 pi r is equal to the total current. And then you solve for the magnetic field. The phi component of your magnetic field is equal to I over 2 pi r. So that's much, much easier than the long derivation that we did earlier. Okay, so that's Ampere's law applied to an infinitely long wire. Same result as a Bio-Savart law. Second example here, I think I'll show you this example real quick. It's actually quite straightforward. So this is an example where we find the magnetic field of a long conductor. So I apologize, I'm probably going to end up going 10 minutes over today. Those of you who need to go to your other class, you can feel free to watch this afterwards. This is something that you're going to need for your homework, so I thought it would be useful for us to go over them now. So again, those of you who need to go, no problem. We won't have any other polling questions here. I'll just go through this example, and that way you can watch it later for the homework that's due on Monday. All right, so in Ampere's law example 2, here we're going to find the magnetic field of a long conductor internal to the conductor and external to the conductor. So in this, just to differentiate it from, or to contrast it from this previous problem, this first example was Ampere's law for an infinitely long wire. And what we did is we found the magnetic field outside of the wire. In this problem, in the next problem, we are actually going to look at the magnetic field inside the wire and outside the wire in both situations, in both areas. Okay, so the problem goes like this. Suppose we have an infinitely long conductor, infinitely long wire. What is the magnetic field inside and outside the wire? So R is less than A and R is greater than A. All right. So R is the radius and A is the dimension, the radius of the wire, and R is just our distance coordinate, our radial coordinate. So our strategy is that we are going to do the same strategy that we did earlier. We're going to apply Ampere's law, and we're going to select an Amperian contour, and then we're going to use Ampere's law to solve for H. But we're going to do this twice. We're going to do it once for R is less than A, and then a second time for R is greater than A. R greater than A, we already did that on the last example, so that's trivial. And then we're going to do it for R is less than A here. All right. So to solve for to apply Ampere's law for R is less than A, we have to first draw an Amperian contour, and our Amperian contour is, for symmetry, for the sake of symmetry, it's a circle on the inside of the wire. The wire is circular, and this Amperian contour is just a circle in the middle, inside of the wire. Why do we choose that? It meets the criteria. The current, some amount of the current is enclosed by the contour, not all of it, but some of it. And you'll see why that's important in just a second. The second criteria is that the magnetic field should be uniform everywhere along this contour, because that makes our integral very simple. So we're going to draw in an Amperian contour on the inside of the wire like this, and then we're going to follow Ampere's law here. All right, so what are the key intuitions? On the interior, there is a magnetic field H phi. Right, whenever you have current through a wire, just take your thumb and point it in the direction of, take your thumb and point it in the direction of the current, and your fingers are going to curl around in the direction of the resulting magnetic field. This is the intuition that you have to have when solving these problems. Whenever you're trying to find magnetic field, just think about whatever direction the current is going, there's going to be a magnetic field going around it. All right, so if your thumb is going in this direction, then the magnetic field vectors, H phi, is going to be going around in a circle like this. And that is the key intuition. And that's also shown here on this on the second portion here. All right. So, applying Ampere's law. All right, so your contour is going to be going around the contour C1. So it's going around this green circle. So it's equal to H dotted with dl. Okay, just like before in the previous example that we did, if the magnetic field is uniform everywhere on this circle, then the line integral around this is just going to be equal to the magnetic field, h phi, times the circumference. Okay, I'll say that again. If the magnetic field is uniform everywhere on this contour, then the integral becomes very, very simple. They're showing you all the steps of the integral here, but I will tell you that it's just equal to the circumference. If the magnetic field is uniform everywhere, it just becomes equal to the circumference times the magnetic field. So this is our h phi. And that's why it simplifies quite a bit. All right, so that's the left-hand side of the equation. Left-hand side. So the right-hand side, we're going to be doing the right-hand side of the equation right now. The right-hand side of the equation, how much current is flowing through this green circle? So how much current through the C1? To find this out, we have to assume that the current flowing through the area enclosed by C1 is equal to the total current I multiplied by the ratio of the area enclosed by C1 to the total cross-sectional area of the wire. In other words, this circle, C1, has an area pi r1 squared. So the area of C1 is equal to pi r1 squared. That's the cross-sectional area there. The area of the entire conductor is equal to pi a squared, right? So all we're doing here, we're saying that the amount of current going through the circle C1 is some fraction of the total current going through the entire wire. Okay, the fraction is equal to the ratio of areas. So the ratio of areas is pi r squared, pi r1 squared over pi a squared. Multiply that by the total current I, and this is the current through C1. So you have the left-hand side of the equation, right-hand side of the equation, and by setting these two equal to each other, we can find a relationship between the magnetic field h phi and the current I. So this is what we come up with here. This is for r is less than a. For r is greater than a, we already found that in the previous example. Right? That's just the magnetic field outside an infinitely long wire. And if we take, if we think about like what happens here, if we think about what the result is, notice inside the conductor, this is for r is less than a, the magnetic field increases linearly with r. A is a constant, I is a constant, but it increases as a function of r. And then once you go outside the conductor, the magnetic field decreases as r. So that's why you get a graph that looks like this. If you were to plot the magnetic field as a function of r, the magnetic field is 0 in the middle because there's no current going through the contour. It increases linearly, increases until we get to the edge of the wire. And once you get to the edge of the wire, as you start going further away, the magnetic field decays as 1 over r. All right. So this is how, you can see that Ampere's law it requires a lot less math, just more intuitive understanding And this can be used to really figure out, really figure out the magnetic fields in different places. Example 3. This is an example where I'm just going to say that this is part of your homework problem. So I would like for you as a homework problem to go through this slide and understand how to calculate the magnetic field inside a toroidal coil. Okay. I actually have this slide here so that your homework is easier to do. It actually walks you through the entire thing, but I'm assigning as a homework problem that you go through this step by step and understand it, so that if you had a test question on it, then that would be fair game. And that's it for today. So I'll just give you a little bit of a hint here. The main thing, the interesting thing I want you to know about this problem is that I want you to develop this intuition of how magnetic fields are generated. As I said, right-hand rule. Point your thumb in the direction of current, and then the magnetic field is going to circulate around there. Okay, so here, I'm just going to draw this in green. So in this portion here, the magnetic field circulates out like this, okay? In this portion here, the current is flowing up, so the magnetic field is like this. Out here, in this portion here, the current is going, I'm sorry, I drew the current in the wrong direction here. Just a second. The current is going in this direction. So by right-hand rule, the magnetic field is going up here and then down here. All right, and you repeat that process for all the segments that you can envision throughout this toroidal coil, and you start adding up the magnetic field, and you'll find that in the toroidal coil, you get this magnetic field that goes in this phi direction. It's enclosed inside the coil. All right, toroidal coils are used in motors, induction motors, and in other situations, so that's why that one's very important. Okay, so I know we stayed extra today, so I appreciate you staying the extra time. And like I said, those who were not able to, you can just watch the recording later. Okay, so any questions today then before we stop the class? Okay. All right, I don't see any questions. So what I ask is that all of you please remind your fellow students who have not done it yet. We need everyone to complete those surveys to find out, to take a poll on the final exam time. We appreciate you if you can do that today. Okay, good luck on the homework. As I said, we'll plan on a 2 p.m. Sunday session for those who want a little bit of extra help on the homework, and that will be done through the video conference here. All right. Have a good weekend, and I will see you all on Sunday.